Hello everyone, I'm Luz Angela Garcia and I'm gonna talk about some exploratory work that we have been doing with FRBs and predicting their host galaxies in the SDSS catalog. To start with, let's say that an FRB or fast radioverse is a transient that lasts for a few milliseconds and it's really bright. It is observed in radio telescopes and they are usually found in between 800 and 1400 megahertz. They are believed to be extragalactic and they are part of a family of different transients that last less than a second. In particular, these objects are quite bright, as you can see here in the diagram on the right, and they are represented in orange in this diagram. And on the left-hand side, you can see the typical cascade or the diagram that represents the detection of an FRB. In the x-axis is the time, and then in the y-axis is the frequency with this FRB is detected. And then you can see here that when the FRB is detected, we have a very large flux that resembles from the noise. And this is particularly interesting because today we don't know exactly what's the origin of the FRBs. However, we know that these astronomical transients happen on a rate of 1,000 FRBs per day. But let me clarify that the intent of this talk is not to study the origin of the FRBs, but instead to try to use them as cosmological proxies for a galaxy host. Now, in the diagram that we have here, it is presented the Lorimer FRB, the first one that was detected in 2007. And once the light from the FRB is released from the object, it starts traveling through the IgM, where there's an homogeneous amount of electrons that cause several scatterings of the photons that were released from the FRB. And these cause a time delay or a difference in between the frequencies. So we have here the typical diagram where it shows the minimum and maximum frequencies of the light. And this is directly related with the number of electrons that are in the line of sight where the light is going before it reaches the radio telescope. So this dispersion measure that we defined in the previous slide is mainly explained by three terms. The first one is the dispersion due to the host galaxies, and it's redshift dependent. Then we have the dispersion due to the electrons in the IgM. And finally, we have a dispersion that it's due to the content of electrons inside the Milky Way, which is more or less that we have here in the diagram on the left. Our sample of FRBs is going to be composed by more than 1,000 FRBs released by different telescopes on Earth in a range of 400 to 800 megahertz. But it is mostly composed by FRBs that had been released by the CHIME collaboration. However, we have a different subsample of FRBs that have been confirmed with an electromagnetic counterpart. Thus, they have a secure redshift. We have proposed a pipeline to identify the possible host galaxy that where the FRB was produced. And our pipeline has several steps. So I'm going to start by briefly discussing the validation with these confirmed FRBs. We look in the literature for different FRBs with secure redshift, in addition to their dispersion measure, their 2D position, and other features that could be used for us to create the models that we use to relate the redshift and the dispersion measure. From these 117 FRBs that are confirmed, we excluded 5 because they are either produced by or they were confirmed to be hosted by a cluster, or because they don't have a good redshift confirmation. Then we start web scraping of Galaxies in the SDSS catalog using these two packages, SQL and Beautiful Soup. And we look for all the galaxies that are inside a 0.15 radius around the position of the FRB. Once we have this list of galaxies per each one of the FRBs that we have confirmed, we compute this probability that's presented there and found 24 FRBs that coincide with the footprint of the SDSS, and compute this probability for each of these FRBs. So this is the list of confirmed FRBs that has a large probability to be hosted by a galaxy in the SDSS. We also compute this correlation between the galaxies that we found in the SDSS catalog with the highest probability, and then the apparent magnitude in the air band. And as found by Agarwal et al. In 2021, there is a positive correlation between the redshift and this magnitude. Interestingly, we found that this correlation follows their theoretical prescriptions with the simulations clade. And also here, I want to stress that the probability is computed here. And we have here also the number of galaxies that we found inside this radius, inside this circumference that is centered in the position of the FRB. Now, we don't have a redshift for the FRBs that have been detected. So we need to have a relation between the dispersion measure and the redshift. So to do so, we want to make sure that our relations or functions are well fitted to the data that we have available for the 112 FRBs that are confirmed. So to do this assessment, we first implemented different models that relate the dispersion measure and the redshift based on different works that we have done in the past. Then we use our 112 confirmed FRBs, and we ran a full bootstrap scheme with different subsamplings. At the end of the day, we found that the best subsampling proportion is 0.95 and 500 realizations. And then we basically determine the best fit parameters for each of these models that I'm going to present, and evaluate the goodness of our results using different statistical metrics as the likelihood, the Bayesian information criterion, the R-square or determination coefficient, and so on. So the first model we explore is a linear model, a linear relation between Z and the DM. And this was first explored by Macquart et al. In 2020. And it was later studied with different subsamples of confirmed FRBs until today. I'm showing the results with the bootstrap that we ran, and it's presented in Garcia et al. 2025. With this bootstrap method and the 112 different observed and confirmed FRBs, we have these best parameters. Then we explore a log-parabolic function. The basic idea behind this is that we can study the dispersion measure of the IgM based on numerical calculations with different simulations. Different groups have assessed this in the past, but I don't have much time to go through all of these works. Basically, this is what we have from numerical works. And the best fit parameters with our bootstrap are presented here. Finally, we also explore a power law function that was also determined by different groups using numerical simulations and different statistical tests. And they propose that basically we can measure the dispersion measure as the largest contribution due to the host galaxy that is presented here, and then an additional term due to the Milky Way. With our bootstrap methodology, we found these best fit parameters. And we also ran a mock test with the confirmed FRBs that are presented in blue dots in the plot on the left. And then the black points are representing the results from our mocks that are related using the Weibull distribution that I'm showing on the right. And we create 100 realizations of different mocks, each one with 500 simulated FRBs, as you can see here in the plot on the left. With this, we are able to relate the DM of unknown or not confirmed FRBs with the redshift from spectroscopic galaxies that have been detected with SDSS. So to do so, we need to acquire and characterize the data from the latest data release from CHIME that has about 1,020 objects. And we cross-match these FRBs. Again, these FRBs don't have a secure redshift, but they have information about their position and also the dispersion measure against the SDSS footprint, resulting in 275 transients. Then we use the probability function that we validate before to search for all the galaxies in the SDSS catalog that are inside the circumference with 0.15 radius, centered in the position of the FRBs, the 275 FRBs. And finally, it was based on different criteria that we impose to rank our models. We identified the galaxies that have more than 0.9 probabilities, and report the one with the largest probability to be the host of these FRBs in the SDSS catalog. With this pipeline, we are able to say that our three models are most probably hosted by the following SDSS catalogs. We report here the FRB, where the galaxy that we think that this galaxy is hosting. These are the two position of the galaxies and the redshift, and also present the redshift of the FRB that we are trying to find their base location, and then the probability of this host and the number of galaxies that are inside the radius. As you can see here from the linear model, that was the best, the one with the highest score in the different statistical metrics. We found 3 possible FRBs that could be hosted by Galaxies in the SDSS catalog. For the second one, that is the log-parabolic function, we found that there are no galaxies in the SDSS catalog that could have hosted the FRBs, the more than 1,000 FRBs from the CHIME, the latest CHIME release. And this is just because they don't match the one of the features, in particular, that their probability is higher than 0.95. Finally, for the power law function, we present 6 FRPs that could be hosted by Galaxies in the SDSS catalog. And we want to stress here that this is just a proposal that could be set to look for host galaxies of FRBs in spectroscopic catalogs. Finally, I want to close my talk by saying that using a preliminary sample that we found and presented in Piratova et al. 2025, and using the likelihood function, we found a value for each knot of 65.13 plus minus 2.5 kilometers per second per megaparsec. And then if we use the same description as I did with the 100 MOX catalogs, we found a value for each knot of 67.30 plus minus 0.91 kilometers per second per megaparsec. This result is consistent with previous found from other groups that have also assessed the value of the Hubble constant, and this is work in progress. So to conclude, I want to say that we have proposed a method to find the host galaxies of FRBs with unknown redshift, and this could be further tested and improved to match with galaxy catalogs with a spectroscopic redshift as DESI, or in the future with Euclid. Thank you very much.